To begin, let me remind you that we have this test coming up, the midterm test, running from Friday at 5 p.m. to Saturday at 5 p.m. And so I will post the questions on Friday at 5, and you should email me your answers by 5 o'clock on Saturday. I think that the time of 24 hours is way more than necessary. And so, it's not designed for you to spend all that time doing it, but it's designed, for you to spend an hour or so during this 24-hour period. I posted the old exams up on Blackboard. I'm writing this one now. I think I'm making it maybe a little bit more challenging than the old one, or maybe I should say, for each question there are some easy parts and some harder parts, and so do what you can with each of them, and so it's not necessary to get 100%, but you want to answer the easy parts and do what you can with the harder ones. Let me just make a comment about tests in graduate school in general, right? So it's a little bit different now from when you were undergraduates, right? So when you're undergraduates, your goal is to get into graduate school. And so you want to get good grades in your courses because that's how you achieve getting into graduate school. So you guys have done that now. When you are a graduate student, your goal, of course, is to get a good job for after graduate school. And the way you achieve that is by doing really well in your research, right? That it's a research degree. And the purpose of courses in graduate school is secondary. Right? The purpose of courses is to teach you what you need in order to do really well in your research. But it's the research, not the course grades, that are going to determine what's next in your career. Courses have a different kind of a role, right? And so you should try to be getting what you can out of this course and out of all your other courses in order to do excellent research in the coming years. So given that, you might ask, why do I bother giving exams and giving you grades? That actually would be a very reasonable question. I guess one answer is that for some students, not all, but some, grades provide a motivation to work hard. And if you work hard, you're likely to learn more. That's normal. And another answer is that grades provide kind of a quick way to summarize how students are doing in the first couple years of graduate school. And so by looking at the list of all of a student's grades, it's possible to for the director of the program, for Dr. Yockley, to identify which students are having trouble in the courses, and that is some indication that maybe some students might want to do a different thing other than getting a PhD. I mean, there are lots of good things to do in life, and sometimes some students might be guided to do other things, and that's fine. Better to find out sooner rather than later. That's what I can say as far as the sort of general considerations. And so No, try to do well, but it, it's not the biggest deal for you, right? The biggest deal is going to be the research coming up. Okay. Any questions about things getting ready for the test? No? Okay.
Will you be available for like, say, tomorrow? Would you, if like someone emailed you for like kind of, just asking questions about like exams and stuff, or about the practice exams, would you be available for tomorrow for consultation by email?
Yeah, yeah. If it's a simple question, I can try to answer by email. If it's a harder question, I'll just schedule a time to do a Zoom meeting. And it's easier for more complicated subjects. I will say that after the class on Friday, I mean, I will have a regular class on Friday, and I'll teach you new stuff in the class on Friday, which will not be on the test, which will not be on this test. It'll be on the final exam. And after the Friday class, I will need to end promptly to go to another appointment. And so don't wait until then to ask me questions. All right, so apart from that, we are talking about the dynamics of phase transitions. And so the question is, when you cross a phase boundary, what happens? That we know when you cross a phase boundary, the equilibrium state changes. So if you wait long enough, you will eventually change into the new equilibrium state. But how do you get from here to there? Right? What's the process of making the change? So the example that we were using to discuss that was for the Ising magnet, where the phase diagram looks like this in terms of field and temperature, and there's a boundary up to the critical point. And then the question was, if we cross like that, so we cross the first order phase transition, then we start with a state that is mostly spin down, and we're changing to a state that's mostly spin up. But how do you get from a state that's mostly spin down to a state that's mostly spin up? And so to describe that, we consider a situation where there's mostly spin down in a material, but you could get a nucleus of spin up. So it's up, surrounded by down. And we say, suppose, for example, that the nucleus is a sphere of radius r. And then we can ask for the free energy as a function of r. And that's what I worked on calculating at the end of the last class. And so for the excess free energy, so I'll say delta F, that is the free energy of the system with the nucleus, minus the free energy of a uniform system. And to be specific, minus a unit of uniform spin down. And so that as a function of r looks like this, right? It goes up and then it comes down. So this is an important plot because it shows we have to wait for a nucleus to form, and we have to wait for a sufficiently large nucleus to form, right? If we form a nucleus, say, with this size, then it tends to reduce its free energy by shrinking. And then it'll just go away down to radius of 0, that is to say, no nucleus at all. By comparison, if we form a large enough nucleus, then it can reduce its free energy by growing. And so then it will grow and continue to grow until it eventually takes over the whole system. So the borderline is this critical radius RC, which we calculated at the end of the last class. And if I look in my notes, it is that RC is equal to 2 sigma over delta free energy density. All right, so this sigma is the surface tension. So it is energy per area. So that's the surface tension associated with the boundary between spin up and spin down. And the delta F is the difference of free energy density. Between up and down. And so this is some energy per volume. So the ratio of those two things then is length. And then we can say if R is less than RC, then it shrinks. And if R is greater than RC, then it grows. So this gives us the dynamic process of nucleation and growth. But first, we have to wait for a nucleus to form, and it has to be a sufficiently big nucleus, bigger than RC. And then there's growth where that nucleus gets bigger and bigger and bigger. Or perhaps there might be more than one nucleus that's growing at the same time. So maybe there'll be, a big box of spin down, and then there'll be some nucleus of spin up over here, and another one forms over there, and they both grow until they come together and take over the whole sample. Now, the important thing about this dynamic process of nucleation and growth is that it takes time. And it doesn't happen instantly. It requires time. And then you're going to ask me, well, how much time does it require? And that's a hard question. I mean, it varies a lot from one system to another. In some systems, it would be a small fraction of a second. In other systems, it could be it could be something that's much greater than experimental timescales, so that you don't actually see it happening. The system is stuck in its metastable state for a long time, for the entire time of an experiment. Now, one common sort of behavior is to see, what happens if you change a magnetic field back and forth. Okay, so that gives the phenomenon of hysteresis. So suppose you change a magnetic field back and forth, and you measure the overall magnetic order of the sample. So the average magnetic order of the whole sample, which might include domains that are up and down. So average for the whole sample. So we know what would happen if we're in equilibrium. Okay. So if we're in equilibrium, this is what we already calculated when we were first talking about the isotope. We found an m as a function of h that would be increasing, and then there's a discontinuity, and then it increases again. Okay, you remember when we found these plots, right, by looking at where's the minimum of the free energy. So this is the plot for equilibrium. That is to say, this is the plot for a very slow experiment. Okay. But now, suppose that we are not in equilibrium. Suppose we want to do the experiment more quickly than that. Okay. Well, I'll draw that in another color. Okay, so in that case, if we start at the negative field and we increase, now we could pass h equals 0, and we still stay in the same well of the potential energy. Right? The potential energy has two minima, and when we pass this point, the two minima cross, right? That the minimum that we used to be in now becomes not the deepest, but only the second deepest. Right? But for some amount of time, we might stay in that minimum. Okay? And so during that time, the experimenter might be increasing the field h. So we get this path coming up. And then eventually, when the nucleation and growth process happens, finally, the other state with the positive magnetization finally takes over. And then the magnetization jumps, and then it continues to grow from there. Now, suppose we are at this high magnetic field, and we do the experiment in reverse. Right? We gradually reduce the magnetic field. So we follow this path back down, but now we keep on going this way because we're in one of these potential energy wells, and even when that potential energy well is dropping down, it's still the equilibrium state. Still, we stay in it all through this range. And then h passes through 0, and we still stay in it. But eventually, the spin down phase is going to be the equilibrium phase, and then it will take over the sample. And so then we'll have the jump discontinuity like that and continue over to more negative values of H. So we get a path that looks like this. It goes up and around there, okay? And then going back, we go there and there and there and there. So this path makes a loop in the plot of M versus H, right? A loop going up like this and then coming back down like that. Okay, so this thing is called a hysteresis loop. And this is something which is in general characteristic of first order transitions. That's a point that Cheng mentioned in one of his questions after class last time, that this is a phenomenon associated with a first order phase transition, because this is the sort of phase transition where there are two distinct minima of the free energy, and it takes time to get from one minimum to the other minimum. But for some range of parameters, both minima are possible. And that's why you can say for a certain range of parameters, you could be going up this way in one direction and coming down this way in the other direction. That works as a function of magnetic field. It also works as a function of temperature, right? There can be experiments where you are heating and you see one phase over some interval of temperature, and then you reverse and you're cooling and you see a different phase over the same interval of temperature, right? Only one of them is the equilibrium phase, the stable phase. The other one is only metastable. And the true equilibrium phase transition is somewhere in the middle, just as, it's somewhere in the middle over here in a plot like that, right? But you have to do the experiment more and more slowly in order to identify the equilibrium phase transition.
Excuse me, a question.
Please.
Does the area of the hysteresis loop depend on the changing rate of the magnetic field?
Yes. So if it were a very slow experiment, you would get a very small loop, right? And so it could be, that if it's a very slow experiment, then the magnetic field would not increase very much past zero when you would eventually see this change, right? And going backwards, if you do a very slow experiment, it could come down like that, right? So with the very slow experiment, it could be a very small loop. With a faster experiment, it could be a much bigger loop.
Okay, thank you.
Mm-hmm.
Does it require that that this loop to be symmetrical all the time?
For a magnetic field transition, I think yes, right? So if the axis here is magnetic field, and there really is a symmetry between positive field, positive magnetic order, and negative field, negative magnetic order. And so I would expect to see a symmetrical loop, right? It's a harder question if you have a different variable that you're changing, right? Like suppose you're changing temperature instead of changing field, right? In that case, there's not really a symmetry between high temperature and low temperature. Those are really different states. And so in that case, it does not need to be symmetrical. It might be approximately symmetrical, but probably not exactly. Or likewise, well, here, I was just about to talk about the liquid and gas, right? So let me just move on to that then, okay? So when we're dealing with the gas and liquid, it's essentially the same story, okay? So we have a phase diagram now in terms of pressure and temperature, okay? So if we draw it with temperature there and pressure there, we know there's a phase boundary ending in a critical point like that at temperature Tc and a pressure PC. Right? And at low pressures, high temperatures, we have the gas phase. And at high pressures, low temperatures, we have the liquid phase. So we can cross this phase boundary by varying either temperature or pressure. All right, we can cross by changing temperature like this, or we can cross by changing pressure like that. All right, either way. And either way, we are starting in a phase that is, say, liquid before the transition. Let's take this example. So if we begin here and we increase up to there, okay? So this is raising the temperature of a liquid, okay? So this is just, you know, what happens when you boil water on the stove. And so you're raising the temperature of a liquid. And so when you cross the phase transition temperature at atmospheric pressure, so that for water, that would be 100 Celsius at atmospheric pressure. And so when you cross that temperature, the equilibrium phase is vapor rather than liquid, gas rather than liquid. But how do you get the gas, right? It's not that when you cross 100 Celsius, instantly your pot of water turns into gas, right? Instead, you know there's a process where the water forms bubbles, right? And then the bubbles escape from the pot and go off into the atmosphere, okay? And so, you know, schematically, if I draw a picture of the pot, and here is liquid, then when you cross 100 Celsius, you might first get some bubble of the gas. And then the bubble could either shrink or grow, right? Now, when we're doing this experiment in gravity, the bubble actually does something else, which is it goes up to the top. But let's leave that aside, okay? So if we were doing it in outer space, right, and in the space station, so that there's no gravity, then the bubble could shrink or grow, okay? And so if the bubble is big enough, it will grow, and then it will take over, right? More of the liquid will transform into the gas phase, okay? And vice versa, if we are cooling, right? If we have a container full of vapor and we reduce the temperature, then there will be little droplets of liquid. And if the droplets are smaller than the critical radius, they will tend to shrink, and you'll just go back to having all gas. If the droplets are bigger than the critical radius, then they will tend to grow, and then you'll get the phase transition into liquid. Okay, so just for vocabulary words, people normally use the word bubble to describe gas surrounded by liquid, and people normally use the word droplet to describe liquid surrounded by gas. But they're both the same idea. That is a nucleus of the new equilibrium phase, which is surrounded by the old metastable phase. Okay, so this would happen, dynamically as a function of temperature or a function of pressure. And there could be a hysteresis loop as a function of temperature or as a function of pressure, right? That is, if you're, say, measuring the density or the volume per molecule as a function of temperature or pressure, as you cross the transition back and forth in either direction, say heating and cooling or increasing and reducing pressure, that there could be a loop in the plot, and it would not necessarily be symmetrical. It could be some sort of asymmetrical loop in the plot that's taking you from one phase to the other, gas to liquid, or liquid to gas. Okay, now, let me add one more aspect of this story. Okay. The phenomenon that I have been describing so far, the phenomenon that I have been describing so far is a phenomenon, well, it's nucleation and growth, but more specifically, people call it homogeneous nucleation. That is to say, every position in the sample is the same. Every position in the sample is equivalent. There's nothing special about any position compared to any other position. There is an alternative which also happens a lot in the world, and that is called heterogeneous nucleation. And that is to say, some positions are different from other positions. So why would some positions be different from others? One common reason is that there are boundaries in a sample. So, if you have a pot of water, there's some places that are right, on the edge of the pot in contact with water, in contact with the metal, right? And there are other places that are just in the middle of the pot, right? Another reason is that there could be some kind of impurities. That is just, dirt in a sample, or roughness somewhere where there are bumpier parts, less bumpy parts. Right? And this effect of heterogeneous nucleation is actually very important for speeding up the nucleation process. That is that if you have dirt or roughness, okay, so if here is a little piece of dirt, okay, and then let's say I have gas everywhere around in the sample, okay, and then I cool the sample into what would be the liquid phase in equilibrium. It could well happen that the liquid can form more quickly right on the dirt particle than it can in the middle of the gas. So you could get a situation where there's liquid right up there against the dirt particle. This would require less energy than forming a droplet of liquid just somewhere in the middle of the gas. It would require less energy because there would be less of a boundary. All right? When you have this droplet of liquid surrounded by gas, right, it has surface area on all sides. And so it has the energy associated with surface tension on all sides of it. That's why you need a sufficiently big droplet in order for it to grow. Right? On the other hand, if you have liquid that's just right up against the particle of dirt, then it doesn't have as much boundary with the gas. Right? It has some, but not as much, because on some sides, it's in contact with the dirt instead of being in contact with the gas. For that reason, the liquid phase forms more quickly this way. And so it is easier to get the liquid that nucleates first on the dirt. And then it can start growing from there. You can build up a large droplet of liquid more quickly that way. So this happens in nature a lot. Really, heterogeneous nucleation is more common than homogeneous nucleation because the world has a lot of dirt in it. And so there's lots of impurities that way. And so this is a very widespread phenomenon in phase transitions. And this is something that people often try to take advantage of on purpose. Right? So one example would be, what if, we have the land here, I'll say here's ground, and here are clouds with lots of water vapor up in the sky, right? And so if we have water vapor up in the sky and there's, not enough rain on the ground for the farmers, right? People might want to induce nucleation of rain droplets in the clouds, right? And so sometimes people might drop particles into the clouds. And so if you have some airplane, comes along this mountain, it's supposed to be a picture of an airplane. And then they fly up and they drop particles into the clouds. And those are meant to serve as nucleation sites for heterogeneous nucleation, so that you will get some particle here, and then water vapor will condense to make the liquid phase around it, and then will drop to the ground and make rain like that. So it's a phenomenon called cloud seeding. So, this happens with wanting to make rain. This happens for other kinds of phenomena where you want to induce phase transitions to happen quickly. One example that is very relevant to industry is if the seed that is the heterogeneous nucleation site, if that is some of the new phase itself. All right, and so people could say, if you have the gas phase and you introduce some liquid, if you start with some liquid, you can then grow more and more liquid around the existing liquid.
Does this mean the droplet of the introduced liquid should be larger than the critical size of the?
Yes.
Thank you.
Yeah. Yes. And so this could be important for industrial processing. For example, for making semiconductor chips for the electronics industry. Sometimes people want to make very perfect crystals of silicon. And so, if they start with a seed crystal, and they put it into the melt, then the seed crystal will grow. And so you can build up some very perfect silicon wafer that way. And so, this is extremely important for the materials industry, for the electronics industry. Let's see. I can mention a couple other examples of this. For a couple other examples. Well, one other example, here, I'll tell you some fiction, okay? The following thing is fiction. It's not true science, okay? But there is a story, there's a novel called Cat's Cradle by Kurt Vonnegut. Have any of you heard of that one, by the way? Some American author from years ago. In this story, the author suggests a fictional idea, okay? This is not true, okay? He says, suppose there is a new phase of water, which we don't know about yet, okay? A phase called ice 9. Right. So this idea is, is based on the scientific fact that there really are lots of different ice phases. Right? There are, water normally forms one certain crystal structure of ice, but at different temperatures and different pressures, it can form different ice phases. Okay, and so what this guy imagines in his science fiction novel is that maybe there's this phase of ice 9, which is actually stable at room temperature and pressure. So at at 300 Kelvin and 1 atmosphere pressure, right? So it's the stable phase of water, but we just haven't formed it yet. So everybody thinks that liquid water is stable, but really imagines liquid water is just metastable. And then if there really were a phase like this of ice 9, that would be very dangerous, right? Because, you know, liquid water would be fine as long as it doesn't come in contact with any ice 9. But if you start with some nucleus of ice 9 that's bigger than the critical radius, right, and you put it into a container of water, then all the liquid water would transform into more ice 9. Okay? If somebody drops it in the ocean, then the whole ocean could turn into ice 9. And then there'd be no more liquid water left on Earth, right? And so this was the theme of this novel, or at least it's the one part of this novel that I remember. As I said, this is science fiction. This is not true, okay? But no, it's a story. And it's a story based on the fact that the author's brother was actually a material scientist who studied phase transitions. And so the writer got the idea from his brother to make up a novel that has a phase transition in it. Then there's another example that is, I won't say it's science fiction, but I'll say it's wrong science. Okay, an example of wrong science is something from, I guess, the 1970s. There was something which was discovered by some, I think they were Russian scientists, that they called polywater. And for a while, people thought that polywater might actually be something like ice 9. It's a liquid water, but it's a very viscous state of water. And for a brief time, scientists were actually worried, you know, maybe something like this ice 9 story would really happen in real life. But in fact, it was just a mistake. It was water with impurities in it instead. For a different example, in that incorrect science, there is something in protein structure. There's an interesting point that proteins can fold into different structures. Right? Whenever you have a protein in a biological material, you know, it has a certain sequence of amino acids. And then, based on the sequence of amino acids going along a chain, the protein will fold into some interesting three-dimensional structure. And then, because of the folded structure, the protein actually performs its important biological function. All right, so it might be a catalyst of some sort for a biochemical reaction. Sometimes proteins have more than one possible structure, right? They can fold one way, or they could fold in a different way. And these are like a stable and metastable states of phases. It might happen that one folded structure is the good biological structure, and another folded structure is dangerous. This is, in fact, the case for some real diseases. Okay? So some real diseases are based on prions, which are proteins folded into the wrong structure. The most famous example of that is mad cow disease. So this is a disease that was famous a few years ago before the coronavirus came along. And it is a disease which is not transmitted by viruses or bacteria, but by these prions, the misfolded proteins. And having some misfolded protein can be a nucleus for the formation of other misfolded protein. And so this is, indeed a disease that is transmitted through a mechanism sort of related to the nucleation and growth in phase transitions. So here at Kent State, we have one professor, John Portman, in the physics department, who's working on protein folding. And so his work is making connection between protein folding and phase transitions, and is kind of in this spirit. Okay, I think that is my story about nucleation and growth and the dynamics of phase transitions. So I'm going to stop here, and in the class on Friday, I'm going to begin with something new, starting to talk about solids. And then that's going to lead us later on into liquid crystals for the semester. So I'll begin that on Friday, but for now I'm happy to answer any questions about this stuff or about the test or whatever else is on your mind. Thanks.